In some situations, energy transfers are perfectly natural. In the conservation of energy examples that we saw before, such as the pendulum, we saw that a mass swinging from side to side has its energy transfer from gravitational potential energy to kinetic energy to gravitational potential energy and back again. Now, human beings have long harnessed energy transformations. We can make energy transfer into other types of energy. This is technology. Here I have a light bulb. In this case, I'm going to make an energy transformation occur. I'm going to allow electricity to flow. Electrical energy transfer is going to bring energy to this light bulb, and it is going to convert that energy into light energy. And that is the useful energy output of this device. Every man-made device has a useful energy output. It is the energy in the form that we wanted it to take. If it is a radio, it would be sound energy. If it was a heater, it would be thermal energy. Here, the useful energy output is the thermal energy. We want this to get hot so that we can all have a cup of tea. But I want you to see this. I have two light bulbs. One of them is an incandescent bulb with a filament, and the other one is an array of LEDs. And I'm going to switch them both on and allow them to run. And you can see they're both on and they're both very bright. They're both producing light. But I want to show you one thing. I'm going to introduce this into the equation. This is a thermal imaging camera. What this does is it detects infrared radiation that you and I would know of as the heat, and it depicts it as an image. And what you can see on this picture, if I hold it up to the camera, is that the bulb on the left is significantly hotter than the bulb on the right. Despite the fact that they are both giving off light, the one on the left is also giving off a lot of heat. And if I focus the target, you can see that the temperature of the top of that bulb is about 120 degrees, whereas the temperature on this bulb is still less than body temperature. So what you can see is as energy is transferred to light energy, the bulb on the left is also transferring some of its electrical energy into heat energy. In this case, well, because we didn't want it to get hot, and the heating of the bulb was not something that we tried to achieve, it obviously is not part of the useful energy output. This, in fact, is wasted energy, energy that we did not intend, but we have created anyway. So to get a handle on the amount of energy that we supplied to the appliance that was usefully used, we need to introduce a new quantity. And we call that quantity efficiency. So that is what we're doing today. Efficiency. Now, unlike other quantities in physics, efficiency doesn't have units in the same way that distance or current or power might have. Efficiency is actually a percentage. It is the percentage of the energy that was usefully used. There is an equation that gives efficiency, and I'm going to write it down now. To start with, our equation is a ratio. And so we're going to draw a fraction in here. What is on the top is the useful energy output. So in the case of the light bulb, that was the light, and the kettle, it was the thermal energy. It is what we wanted it to do with that energy. And we need to divide that by all of the energy that we put in, all of the electrical energy that we supplied, the total input energy. Now, so long as we're not creating any energy out of nowhere, which is impossible, we should always find that this one is either equal to or less than this one, which means this will always equal a number less than the number 1. And equaling a number less than number 1, it could be 0.5 if this was half of that. But what we want to do is we want to express it in a way that's more friendly to people. And people really understand things if they're expressed as a percentage, where 100 is full and 0% is not at all, with 50% meaning half. So if we times this by 100%, this whole thing becomes a percentage. Now, there's nothing to fear here. This is exactly the same as what you might have used to work out your percentage score from some assignment or test. If you got 50 marks out of 30 available to you in that exam, or 15 divided by 30 times 100 would give 50%. Here it is exactly the same. It's what you got divided by what you could have got times by 100. An example here could be that my useful energy output could have been equal to 50 joules. But let's say I put in far more energy than that to start with. The total energy input let's say that was equal to 150 joules. My calculation would be 50, so my efficiency would be 50 divided by 150, which is equal to 1/3. So times 100% would give 33.3% efficient. That is how we calculate it. But I think we now need to look at some specific examples to make this really clear. Here is an example. This is an example based on the story of Rapunzel. In the story of Rapunzel, Rapunzel lets down her hair and pulls people up to the top of her tower. Now, we're not going to quite inflict that upon Rapunzel, but we are going to pull Rapunzel up, in this case, by her hair. And what we want to do is we want to see how much energy a motor takes to do this. Because, you know, it's the 21st century. No one will just pull someone. We need a motor to do it. And we also want to see how much energy is actually transferred in lifting her that physical distance. So we have these two numbers, the energy that it physically takes and the energy that is transferred by the motor in doing so. And this is going to help us to find the efficiency. Now, the very first thing that we need to do is record Rapunzel's mass. Now, it's very, very rude to ask a lady how heavy she is, but yeah, well, she'll use the scales, okay? For the sake of this investigation, she's fine with it, okay? Okay. 104 grams. So before we go any further, we need to record her mass somewhere for later. So we'll put it here. 104 grams, which was 0.104 kilograms. Now, when we look at this equation, we need to understand what is going in and what is coming out. Now, the total input energy is going to be the energy supplied by the motor, or supplied to the motor, I should say. So the efficiency is going to be energy supplied to the motor. That is the total input energy, and on the top line is the amount of energy that we got out, which was her gain in gravitational potential energy as she's brought to the top. So the gain in gravitational potential energy is on the top line, and of course times by 100%. Now here we can use a joule meter to tell us the amount of energy supplied to Rapunzel in pulling her up. We can also work out what the gain in the potential energy is by measuring how high it is, knowing her mass, and applying the formula that potential energy is equal to mgh. We know m, and we'll know h when we measure it. So let's measure it. The next part of the process is we need the height of the drop that we are lifting her up. And so we use this very large tape measure and measure how far it is from the ground floor up to where we are right now. Comes out at 8 meters and 80 centimeters. So this gives us our height. Height is equal to 8.8 meters. So what we're going to have is our mgh on this top line, mgh. We now know all of these numbers. We know that the mass of Rapunzel is 0.104 kilograms, that the gravitational field strength is 9.8, and the height that we have to lift her is 8.8 meters. Now we need to measure the amount of energy a motor takes pulling her through that distance. So let me explain to you my apparatus. So this is the apparatus we're going to use. What is here? Well, to start with, a power pack to deliver electrical energy to the motor. There is a switch. The pressing of this switch will enable me to operate and allow the electricity to flow. Now, in the circuit, we also have a joule meter, and this will tell us exactly how much energy it takes to pull Rapunzel from the ground floor all the way up here. These are plugged into a motor. And on the motor is this big reel of string that is going to do the pulling. The string pulls Rapunzel directly up through this over here. So the first thing we have to do is we have to attach Rapunzel to the string. And here we have it, Rapunzel attached to the string by her hair. Right, time to go down. $230 joules. 230 joules, well, this is the energy supplied to the motor. So we can rub this out and put in 230 joules. Now it's a case of working this out. The top line is 0.104 times 9.8 times 8.8, and the answer is 8.96 joules. That Rapunzel only gained 8.96 joules when 230 joules was spent bringing her up to the top. So clearly, this is not very efficient. If I divide 8.96 joules by 230, and then times 100, my motor is only equal to 3.6 3.9% efficient. Only 3.9% of the energy that the motor had turned into the storing of gravitational potential energy by Rapunzel. So where did all the extra energy go? Perhaps the most obvious place that some of that energy has been wasted is in sound energy. Another source of wasted energy could be heat. And you can see I have a thermal imaging camera, and I'm going to point it at the apparatus and set it going, and what we should see is that actually some of the energy is being lost to thermal energy. Here we go. And you can see the friction is warming up parts of that, it's starting to glow. So 3.9% efficient when you compare the amount of energy stored to how much energy was transferred. But there's one more thing that we need to talk about, and that's what happens when we involve this, time. You see, we spoke about power a little while ago. Power is defined at the rate at which work is done, or that energy is transferred. And power can also fit into this formula for efficiency. This next bit is complicated, but I want you to try. Now, if we were to consider power instead of energy, then we would need to modify our formula. Now remember this key fact, that all power is the rate at which work is done. And work is the energy transfer that we are in fact witnessing. So power is the amount of work that is done divided by the time. Now what we could do with the Rapunzel is we could modify this equation. We'll get rid of all our workings out from before. We'll remember that it was equal to 3.9 because hopefully we should get a similar answer if we do it in terms of power. But what we need to look at up here is that it's now slightly different. Rather than the useful energy output, we have to think about the power, the amount of joules every second that is going into lifting Rapunzel up. So this is the useful power. So this is the power, this is the work done in a useful way. So it's the useful power divided by the total power. Or, if you don't like that, we could say the input power. Now, first of all, the useful power. Well, the useful power is the work done per unit time. And how we're going to calculate this is look at how much energy was transferred in pulling Rapunzel up, which is how much energy is stored in gravitational potential energy, which EP is equal to mgh. So mgh divided by time would give us how much useful power was being produced. But this would be averaged over the whole journey from the ground floor to the top. It's not measured at any precise moment, it's just a case of dividing all of that stored energy by the number of seconds. So between each second interval we worked out how much work was usefully done. Down here, the input power is exactly the same as before, except it's the electrical energy that went in divided by the time taken. So what we need to do is repeat the experiment, but record the time. Now what you should notice is that the input power, being the electrical energy divided by time, is that if we have time here and here, the time is going to cancel out. And it should equal 3.9 still. But we can check it, because we don't necessarily have to believe. Let's go see. So now we'll see how long it takes. .72 seconds. So when we include that in our calculation and we take the MGH, we're going to now divide it by 7.72. So for MGH, we'd have to multiply her mass, which is 0.104, by 9.8 by the 8.8, which is MGH. And then we would have to divide it by the time that it has taken, 7.7 seconds. And we come out with the amount of work done against gravity. Every single one of those seconds is 1.16 joules, which means that the amount of useful power that this thing is applying is 1.16 watts of power. Now remember that number, it's going to be important in a second. So now we need to work out what the output power of this motor was. And so what we're going to do is we're going to pull up Rapunzel and look at the total amount of energy that took, and we're going to also record the time again, and we're going to divide this energy by the time, and hopefully what we should then end up is a measurement of the power as averaged over this whole couple of seconds. So here we go. We'll pull her up in 3, 2, 1, and okay, so it took 10 seconds and 32. And I think I was a bit slow on the old draw there, so I don't think I perhaps timed it so accurately, but we can still work with that. 289 joules. 289 joules divided by 10.32 seconds means that the power output of this motor was actually 28 watts. 28 watts. So does 28 watts seem reasonable? It is of course averaged over the whole trip. My timings might be slightly inaccurate and that might cause a small difference in this efficiency as calculated through the power than when we calculated it through energy. But I have a way of checking. This device tells me the power output. Now it basically just measures how many joules are used each second and then displays it here. We should find that this should equal that if I got it right. Let's see how close I got. Interesting. This thought 48. Now why did it think a higher amount of power was being used? Well, best explanation was I didn't time it very accurately when she came up. I divided by too high a number, that I didn't stop my stopwatch for about a second after the point where she reached the top. But you can see how these different ways of measuring it could come up with slightly different answers, and therefore the efficiency as calculated through the power may be ever so slightly different from the efficiency as measured through the energy. So let's go see what it equals. So let's take a little look. If I take 1.16, which was the amount of power usefully used in making her gain all of that gravitational potential energy, divided by 28 and times it by 100, I find that through this method my efficiency is equal to 4.1%. It's actually very similar. And you can see that as calculated through the power method and calculated through the energy method, it's approximately the same. Why is that? Well, it's because time was involved both on the numerator and the denominator, this fraction, and so it just cancelled out. It does not matter whether or not you calculate efficiency through power or energy. What it gives you is a measurement of just how much of the energy supplied by that device is being usefully used.